don't think
That's why he said I could have his position.
Okay.
Hi, good morning, everybody. Good afternoon. All of you. If I were working, I'd be asleep, so. I'd like to today start our journey into formalizing kind of the rules of this course, quantum mechanics. The last semester we talked about the laws of the, I didn't really call them that. Yet these principles that we use from dynamics. You know, the energy needed to be minimum, entropy needed to be maximum, and all of these things. Well, quantum mechanics, microscopic rules have the same kinds of laws, but there's a little bit of ambiguity in that. We can actually make a choice about how we want to interpret certain behavior of the microscopic system. And so we have to make a choice about how we interpret it. I'll talk very briefly about that. But ultimately, what we've kind of learned in the last few classes is that we have this. Let's just go back to the electron with its color and its flavor. That we have this object that we can measure certain things about that are fixed in time, right? Once a white electron is white, it's always white. So we do something else. But the best thing that we can do if we haven't measured anything is to assign probabilities, right? When an electron goes into our box, the entire point of problem set one is that you don't really know anything about it. And so therefore it's everything all at once. Like the great movie, if you haven't seen it. And electrons are in that way, in some sense, when you don't measure them everywhere, everything everywhere all at once. And so we need to formalize that. But it's very hard for us to physically kind of visualize something that is everything. That suddenly is something once you measure. So the point of quantum mechanics, when we're talking about these vectors and these matrices, for instance, that are not physical representations of the molecule or the atom, the electron, or the box. I mean, they're physical objects in the sense that an electron is a charged particle, and in fact, a color box is just a series of magnetic fields. Flavor box is the same way. And so there's some physical mechanical operation that you're doing that really doesn't have anything to do with vectors and matrices. But the results of that experiment, the results of your measurements, the results themselves, the things that you measure, not the actual object, the identity of the object, but rather the results of your measurement, are the things that you read out from the vector and the matrix. They tell you what the potential results of your measurement are. Right? Put an electron into a color box. 50% of the time it's white, 50% of the time it's black. The way we represent an electron is half white, half black. That doesn't mean that the electron is actually half white and half black. It's just the way math works out. Right, so here the laws are a framework for us to interpret measurements. We can't touch and feel an electron. I mean, by definition, we can't because it doesn't have a physical size. It has a mass and a charge. It can exert some force or some momentum, but we can't touch it or feel it. But we certainly know it exists because we can measure it. Okay. So quantum mechanics and what we're talking about this semester is a mathematical representation of what we measure in the lab. It's a mathematical framework for understanding what we read out in the lab. But all we know about these little objects are what our box looks like. We're not touching the electron. All we're reading out is a 1 or a -1 that's black and white. So the numbers, the vectors, and the matrices represent the possibilities of the results we get and the operations we do to the object to get those results. So it's a way to explain the measurements themselves. And therefore, depending on what measurement we choose, we have a different perspective on that object. I'm going to try to drive that point home today. That we can choose. We have to choose how we want to measure an object, how we want to interact with it. Say in spectroscopy, we interact with it with light. Light to interact with an electron or an atom. And we can devise a perspective on that atom molecule that we're interacting with light by using mathematics to represent the potential outcomes that we get when we shine a light at an atom. So the theory perfectly explains to very, very high precision the exact results that we get, but doesn't really give us a physical touch healing or construction, what an electron would be like if we could actually touch it. That's not what it's telling us. Rather, it's just telling us what our experiments may show. Way to describe a model to describe the experimental results. And it's a model that works perfect. So let's talk about that model today. Right? Every quantum mechanical problem, atom, molecule, electron, and even people have done it with things as large as mirrors, large macroscopic size mirrors, they follow certain principles, certain rules that the time evolution, the dynamics, and the behavior of these species, whatever it may be, all follow these rules. Very, very high precision. So if we understand those rules, and then what we can do is apply those rules to a specific problem we want to solve, say the structure of the hydrogen atom, or the spectra of a molecule, we know a way to construct that problem, that model, and then solve it, and then think about it, and then calculate what the predicted results of that experiment are. And so it's a way for us to calculate results, because that's all we can do. All we can do is just measure what our reality is on our clocks. That's right. So let's do that. Right. This is going to be about a 2-lecture sequence. It's going to take us a little bit to get through it because I'm going to walk through it very slowly. It's about 5 principles, 5 laws, 5 rules that we have to go through that every microscopic system satisfies. And this will be enough, a complete picture for us to construct anything we want. Some reason. Let's see. Thank you. Okay. Let's do that. So these are what they're called, what we're going to talk about the next 2 days with plenty of examples of what are called the postulates. That's an important word. We'll have to think of that. Quantum mechanics. And the word postulate is a very important word here. There's an important reason why we don't use the word law, because this is an interpretation. It's an interpretive statement. It's a set of statements that we use that we assume are true. But there turns out there's equivalent sets of these rules that we can use that are slightly different, a different perspective on them that give us the same results. Okay, so there's different ways to look at the same thing, different interpretations. Just like when we read a book. Sometimes when we read a book, take an English class, right? Sometimes you interpret that book in a feminist point of view, or a Marxist point of view, or a deconstructionist point of view, literary criticism. And in quantum mechanics, we have similar trains of thought, if you will. How do you interpret the results of an experiment? And there's different ways of thinking about it. Some are very useful for calculations and for measurements and experiments, but they have weaknesses. And we saw one of those weaknesses, right? In the homework, this whole idea that an electron can be both black and white at the same time. A lot of people have a problem with that concept, right? If you've ever heard of Schrodinger's cat, right? The cat is alive or dead in the box until you measure it. It's both. That was Erwin Schrodinger telling you, this is silly. He didn't actually believe that. He thought it was an absurdity and assumed that it was incomplete. It turned out that it's perfectly reasonable to think that this cat is alive or dead if the cat were a microscopic object. So you've heard that, and people have a problem with that. So there are other ways to interpret the results. Interpret this dead or alive idea that don't give you this kind of apparent paradox about logic, right? About a cat being alive and dead at the same time. Right? There's other ways to interpret it. The problem with those other ways to interpret it, they might simplify that paradox, but they become very hard to calculate it. And in chemistry, we're practical. We want to calculate stuff. We have real molecules and real atoms that we want to do stuff with. And we want them to be useful for us. So we're going to choose this interpretation that gives us the easiest way for us to get results out. Okay? We don't have to worry about the philosophy and multiple universes and all of this junk. If you've ever watched any Marvel movies, you know, you've probably heard some of these terms before. They butcher all of them. Actually, so Avengers Endgame does okay with time travel, pretty good. Quantum, what's that stupid Doctor Strange movie called?
Multiverse of Madness.
Yeah, that one. That movie does not do a very good job. But you have this kind of idea, and one of the interpretations of Schrodinger's cat is what's called the many worlds interpretation, which is that this cat is actually that it's not that the cat's result is ambiguous. It's rather that there are two timelines, and the cat is simultaneously traveling along those two timelines, one alive and one dead. And then when you make that measurement, you choose one of the timelines, right? So the idea is that every binary choice creates a branching universe. And ultimately, you fall along one of those timelines. The timeline moves in one direction. And so you can resolve some of these paradoxes that way by thinking, okay, well, I'm creating little logical universes every time I make a decision, but it's very hard to do calculations. It's not very easy to do anything. But we're not going to worry about that. We're just going to assume that electrons act very strangely. And that's the fact of life. And it turns out you can calculate everything you want about them very easily. You just make that, you can just accept that fact of life, that things are a little weird. Stop it from. Yeah, definitely don't take your quantum mechanics from Marvel. It's not a good job. But that's okay. All right, so let's talk about the postulates today. So the first one you've kind of already seen, but let's just formalize it a bit. Right? The first postulate is what's called the wave function. The existence of the wave function. Right? We've seen wave functions already. There are these vectors that represent our system. And so these are just very general statements. We'll kind of look at the consequences today. And so the postulate for the wave function is this. A state of a quantum mechanical system, such as an atom. And again, when I say quantum mechanical, we'll define this. I mean small, microscopic. And we have a threshold for that. I think we'll have some time to talk about it today. If not, we'll do it on Tuesday. It is completely defined, or let's say completely specified by its wave function. Which is a function. It may be a vector. We'll talk about the difference in a second. And we always label the wave function with the Greek letter psi. We have this function psi. And in this class, we're going to be thinking about functions in terms of position. Now, we haven't talked about wave functions in terms of position yet. We've only talked about wave functions in terms of color and flavor, like these little binary properties. But imagine we have an electron in a box. That's this room, right? We might want to track the electron. So we may want to represent this electron in terms of its position. Right? And that's going to be very useful for us in this class. We'll have to think about the structure of this wave function. So we have some position r and of course some time t. Right? So r here is just a vector x, y, z pointing in some direction, and t is time. Okay, so again, now what I represent, this is a very generic, right? We can replace r with any variable that we can measure, right? So for instance, color is psi of a color, right? It's either white or black, a 1 or a 0. This variable can be anything we can measure. It's our measure. And we can define, as we saw, we can define a wave function in terms of its color. That's the wave function in terms of the color, 1 or 0, or it can be in terms of the flavor, 1 or 0. We can choose either one we want. And the same way, we can also choose a wave function to talk about the distance, the position of it in a box or space. So let's think about that a little bit. What does that look like? Right? Why is it a function? Right? Why do I write it as a function? What do we know about functions? Well, functions are defined at every point. Right? Think about, again, this box or this room. Okay, so let's just draw that really quickly. It's very, very simple representation. Right, so let's imagine our room containing one atom. Right, we have this really, really boring room. Of course, this room contains 10 to the 26 atoms or something like that, but not worry about that. And so we can like, let's imagine that it's a one dimension, right? So we're following an electron along one of the lines between the tiles. All right, maybe it's stuck between these two tiles. Okay? We're just gonna do one dimension. Okay, we're not gonna worry about 3 dimensions just yet. It's not that hard to go from 1 to 3. But just imagine that the electron is running along one of these split lines, these lines between the tiles on one end. And that's it, it's staying on that line. And it can move around. All right, so let's go ahead and let's just draw that, right? We have some x-axis. This is our x direction. And here's the door. And here's the wall. All right, and now what I want to do is I want to do an experiment, right? I let that electron go. It's moving around in time. Maybe it's bouncing, maybe it's stationary. I don't know. And I wanted to know where it is. Okay, so how would I measure that? Well, I'm going to put a little detector. Little detectors at intervals along my line. Right? Let's say, for instance, at the intersection where 4 tiles meet, I put a little detector. Okay? And every time the electron passes that detector, the detector makes a ping. Okay? The electron goes right here, ping, and then it turns off. It's the next one, ping, so on. Right? And I just sit here for the entire class, allowing this electron to bounce back and forth, and I count how many pings I get at each of my detectors along the line. All right, so let's just say there's some number of detectors, and we'll label them x1, x2, x3, all the way, let's just say to xn minus 1 and x sub n. Okay, so I've got n detectors. These are my little detectors. And what they do is they ping. They return a 1, right? So let's just say that, right? So these detectors, the detector X, I'm going to put a little hat on top of them to represent my little boxes. And we always put little hats on our boxes. The idea is that X1, let's say X to the I, so the I detector, when it measures psi, right, so this is a position box being with an input of our wave function for our electron. It spits out 2 results. One, if it spits out the position, x sub I, if the electron is at x sub I, right? So let's say psi of x, if x is equal to x sub I, or 0 otherwise. Okay. So my little box will spit out the position name or just a 1, right? I can divide everything by x sub I. So you're going to spit a 1 or a 0 out. Okay, which is big. And then if it's not there, it doesn't pay. So now what I'm going to do is I'm going to count. I'm just going to do a histogram. I'm going to count how many times each of my detectors ping over the course of an hour, over the course of the day. All right, so maybe we find that at the edges, the electron doesn't like to hang out very much, right? So maybe we find some pings here, a little bit there, a little bit here. So the y-axis here, or our electron counts. How many electrons we count? Right. So maybe on the ends doesn't like to sit, but as we start to get towards the middle of the room, it's more likely to be there. And so maybe we get some peaking here, and maybe it decreases on the way down. Well, it could be somewhere, and it's randomly distributed, right? Don't really know what the distribution looks like, but we can model it, right? This is just basic statistics, right? We can measure an average from this. We can measure a standard deviation. We can do all the statistics we want. This is a statistical distribution. That is, given a set of results, how many of the times do you get that result? Right? You do probabilities. All right, so let's now take this perspective, right? We have this thing. What would this look like as a vector? What would psi look like in the position basis, right? So now we're not looking at the color of the electron, right? Our labels for the electron are not colors, but rather they're the locations. And each of these locations, the data tells me the probability. Tells me the probability of being at that location, right? Just like how in the color basis in homework 1, what we've been talking about, that the vector tells you the probability of that electron being one color or another, right? That's what those coefficients are in vectors, just the probabilities. So we can write a vector for this, right? So psi in this case could be written as a vector that's n components long, right? Because there's n possibilities. And what are the components? Well, the components of that are the amplitudes at each of these points. So let's call this, for instance, this would be psi, let's just say, for instance, psi of x sub 3. And this is psi of x n minus 1. Well, it's actually the square. This is probability, so let me square that. So it's psi squared. Remember, remember that we take the coefficient squared probabilities, right? 1 over the square root of, for white plus black, we have coefficients of 1 over the square root of 2. Note the squares of those are the probabilities. So each one of these are the probabilities here. Right, and that means then that the wave function is just psi evaluated at x sub 1, psi evaluated at x sub 2, all the way down to psi evaluated at x sub n. How many times we detected the probability is the square of the vector at that position, right? The coefficient squared of that basis function. That's the value psi squared, so that means the wave function is just the values, like the square root of these. Just take the square root of the probabilities and you get the vector out. So then what is the X box? What's the structure of the measurement we're doing? This X sub I. And what does that look like? What is our measurement vector? Well, what our measurement vector says is that we have n detectors. Okay, so we're going to have an n by n matrix. Just like we saw with color, we have two options, so 2 by 2. Here we have n options. This would be n by n. And what does it tell us? Well, it tells us that if an electron is at, say, x sub 1, then there's no probability it's at x sub 2 or x sub 3 or xn minus 1. All right. So every time an electron passes x sub 1 and it pings, we know exactly where it's at precisely. Okay, so what that means is that the probability, let's just look at it, right? So if we have an electron, so if we look at the electron at position 1, right, the component at position 1, there's a 1 here at the x sub 1 position, and then zeros everywhere else. Right, that's a perfectly localized electron. And so if an electron is perfectly localized at x sub 1, there's no probabilities at x sub 2 or x sub 3 or xn minus 1 or x sub n. So therefore, this matrix only has elements along the diagonal. So if you bring in an electron, if you measure an electron localized at x1, you're not going to get a vector out that's pointing towards x2 or x3, right? Because it's completely localized. Exactly at x1, there's going to be no components after you measure it in other directions. So this matrix should be completely diagonal. There should be nothing on the sides. It should just be one. It should just be all along the middle diagonal. And so our operator or our matrix for X is a big honking matrix. Yes, it's n by n. And when you measure, right, when you measure an electron at x of 1, it just returns the label. Just says, hey, I'm at x of 1. I'm at x of 2, it returns x of 2. So the values of this matrix are just the coordinates. So it'll be x of 1 here, x of 2, dot, 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 all the way to x of n, and everything else are zeros. And that just says, basically, if we have an electron purely at x sub 1, it can't be anywhere else. When you bring in this vector and multiply it by this matrix, you have zeros everywhere except the first row. So the only thing that gets multiplied by a non-zero value is x sub 1. The product of x phi is just x sub 1 times phi. Right? Just like we want. Okay, so we can do this, right? We could certainly construct any wave function for any system we want by building a box in detectors. But there's a problem. This is experimental and it's discrete in the sense that we can only know information about it at these end plots, right? Each of the intersections of the tiles. But what about in between the tiles? I got no knowledge in between the tiles in this setup. And so I don't really know if it's here or here necessarily. In fact, if I measure an x2, I don't really know if it's going to be in the next step here or here. I got no way to tell. I'd have to wait for the next click. But as we know, these things are random. So if it's at x2 and it shows up at x3, there might be some probability that as it moves, it might go to x1. I don't know. So what I'm going to start doing is adding more detectors. Right, so let's just keep adding. Right, I want to be as precise as possible with my measurement. So let's just start adding more. Right, I'm just going to add more tick marks. With different detectors. Right? Think about this now. Now take this to the logical extreme. Now I have all of this additional resolution. All these ticks, my vector is now millions of entries, and my matrix is absolutely massive. It takes the entire hard drive to store it. But I still have gaps. So we're going to go fill them in. Right? And so if I want to understand the entire system, I want to know exactly the probability of the electron across the entire box found in gaps. I have to infinite. Right? There's an infinite number of points between the door and the window. Right? So what does that mean? So take this to the logical extreme. So n will go to infinity. And therefore phi is infinite dimensional. Now, I know you guys, some of you might think I like inflicting mathematical pain. And I'll tell you one thing that I've been as sadistic as I may be, I would never make you dot an infinite dimensional matrix with an infinite dimensional vector, right? That homework would take an infinite amount of time. Right? So we don't want to do that, right? We can imagine that we have a system where we can track every point. It shouldn't be that hard. But we can't use this vector approach. We can't do any calculations over an infinite number of basis points. So we got to think of a better way to represent things in this situation. The continuous space, continuous property like this. It doesn't just have binary. But maybe it's not so hard to think now how we can do that. Because now in my kind of finely gradiated detector matrix, maybe I can start to see that there's some structure to this wave function. Something like that. Who knows? It could be anything, right? And you can imagine now, if I take the distance between each of these detectors to go to 0, what have I done? Well, I've drawn a function, right? I've made a continuous function. I'll just kind of sketch over it, right? It looks kind of like this. Something like that, right? So at infinite amounts of time, an infinite amount of detectors, I've gone from from something that is represented by a very long vector to something that's just a function of the position. Right? So we can just call this instead, well, this would be phi squared of some continuous parameter x, just the position. Well, it's very easy for me to write down functions. They're designed to be continuous. Right? It's easy to write down a continuous function. Maybe this isn't simple enough. And we know how to handle functions. Right? We want to calculate properties of functions. What do? Well, we can take their derivative, we can integrate them, we can multiply them together. We can do everything that we can do with any old functions that you learn in calculus. And what we can do is drop this linear algebra approach, this matrix and integral, this whole thing is that we can drop this matrix and vector approach and then treat everything like functions. So wave functions will be, right? That's why they're called wave functions, is because they have some functional form in a continuous infinite space, like position, something that is infinitely variable. Have some functional form underlying everything. If we project our system into a measurement that's continuous, measured as a function. Right? That'll be very, very useful for us. Because when we think about, say, for instance, the hydrogen atom, we're going to want to think about how the electrons are moving around the proton, like the different orbitals. What you guys know these things: 1s, 2s, 2p, orbitals of hydrogen. But these are objects, if you will, distributions of space where the electron can exist at a certain energy. And those are continuous functions. They can be at some angle and some distance from the center of the atom. And so it's going to be very useful in those situations to write a function down, to do all the math with functions, because the electron can exist in many, many, many infinitely different points around the proton. So the nice thing is that we can always choose which perspective. We have something that's very convenient to be vectors, something where there are a finite number, a countable number of options. And color, vectors work great. But if we want to measure position, and when we talk about energy, position is going to become very important. We're going to want to switch to function. Use calculus. We'll use calculus. We'll use integrals and derivatives. So we go through this class. I'll try to make sure to show you the comparison of what these types of operations look like, right? Where we take a vector and multiply it by a matrix. What does that look like when we have functions? The difference. If a matrix is a function and a vector is a function, we just multiply them together. I'm sorry, excuse me. All right, so we'll have to think about that. Any questions? Okay. Now we haven't figured out how to construct this yet, but we better. Once we have all these rules down, we'll be calculating these wave functions for all sorts of problems. We'll have a really, really defined prescription on how to do these things. Okay. So let's look at one thing that we can compare between the vector approach and the function approach. Right? Different properties that align. Right, so let's imagine now, let's just look at a three-dimensional box for a second. best box in the world. Not really quite sure what orientation is. But let's right, so we have got this 3D box, just like we have in our room. Let's put an electron or a particle in it, right? So we've got some inside of here. We have some psi of x, y, and z. Okay, so here's my little particle. One particle. And now I want to do the detector problem again. And I want to think about, let's just kind of subdivide this box just like we did with the floor. Let's subdivide the box into smaller boxes. So imagine I take a little corner here. A corner there. And let's give this some size. All right, we'll say that the length of this box is Lx, height is Ly, and the depth is Lz. Right? And the width of this little box, the volume of this little box is dx by dy by dz. And I want to ask the question now, what's the probability that I find the particle in this little box? Great question. So what's the probability? Let's just write that. The probability of psi and dx, dy, dz. Well, I've got a bunch of little tiny, right? Let's think about it like in a discretized sense. I've got a bunch of little boxes in here, little detectors in here. Right? So some tiny amount, but a few detectors in here. A few detectors going this way, this way, this way. And if the electrons in there, they'll ping, right? And so the total probability, if this were a vector in the vector space, let's say, for instance, in vectors, if dx spans 3 detectors, which we'll call x sub I plus 1 and x sub I plus 2. All right, so there's 3 little detectors in here, like that. Okay. What's the probability that the electron that passes along one of those 3 detectors? Well, the probability will be the sum from I to I plus 2 of the wave function squared at that position x sub I. Right, so, right, we track the probabilities. The probabilities are the squares of the components of the wave function. Right, we saw that in the previous slide. Squares are just the ticks, how many ticks you get. Right, so the total probability is the total number of ticks. So what happens now to this calculation? Psi squared, sum over psi squared of all my ticks. What happens to this calculation when I take the distance between each tick, each detector to be infinitely small? Right, when I have an infinity or an infinite number of detectors in that region. Right, well, what happens, right? So what I'm doing now is I'm taking a sum of y values on a function and making the gap between them smaller and smaller and smaller. So what I'm doing is I'm taking a sum to an integral. That's all an integral is. It's a sum over function where the distance between the places you take the sum goes to 0. From an integral. So this is going to become an integral. And so the probability in dx dy dz, just write like dx dy dz, is going to be the square of the wave function, which is a function of x, y, z, squared times the volume element of that area, which is dx dy dt. What I'm doing is I'm summing over all the little probabilities and amplitude in the space. And my space is volume this big. I need to add a dx here, sorry. So that says the probability in that tiny little box is this function, psi squared dx by dz. So what is it for the entire box? Well, I'm just going to integrate over the entire thing. Right, so the probability of finding the electron anywhere this is probability is going to be the integral over the box, whatever the bounds of the box are, times psi squared. Psi squared xyz squared dx dy dz. And right, and so this is like, right, if we think about this as being a sum in the discrete space, if this is a sum over all the detectors and their counts, this is summing over all the components of the vector across the entire box. And therefore, what we're doing is just measuring the length of the vector. Right? When we just sum the squares of the components of the vector, that's the length squared of the vector. Magnitude of the vector, how long it is. And the length of any vector in quantum mechanics is 1. Right? So if I do this sum over the entire box, all the detectors in the box, I'll get 1 out, right? Because that all I'm asking is, what's the probability of finding the atom anywhere in the box? I'm asking every detector. That has to be 1 by definition. 100% chance. Therefore, by the same logic, this integral must also be 1. Right, so what this is very important. What it says is that whatever our function may be that represents our electron or our system, doesn't matter what it is, but if it has a wave function that represents that particle, the square of it has to integrate to 1 over the entire space by definition. So we have a special name for this. I'll write this down kind of qualitatively. Any wave function valid, sorry, let me put valid before wave function. Valid wave function must be normalized. The word is normalized, which is just this quality, which is that the integral of the wave function over the entire space of the system times dx or dy dz has to be equal to 1. That limits us to what functions represent real systems quite a bit. Because, for instance, if we imagine this room were very, very large, and we said, hey, maybe the wave function for this molecule is x squared. It's a dumb choice, but just a guess. It could be anything, right? It could be a line, it could be an x squared. But the problem with x squared is that x squared integrated over a large box. As the box gets larger and larger and larger, that function, when you integrate it squared, that's x to the 4th, it goes to infinity, right? It never converges to a value. So the only proper wave functions are ones that when you integrate them over, say, an infinitely large box, integrate to a specific value. They're convergent integrals. Convergent integrals. That limits us to the kind of functions we can use. Right? We can't have functions that just grow and grow and grow forever because the integral diverges. So we have to have functions that go to 0 eventually at some distance. Like they kind of peak in the middle somewhere, perhaps, but at the edges they have to go to 0 because otherwise they wouldn't integrate to 1. So that really limits us. This is the same thing as saying that the vectors have to be length 1. That the wave function version of it, function version the square of it has to integrate. The magnitude of the wave function over the entire space is equal to 1. which means that there's 100% probability of finding it anywhere in space. So this will be really helpful for us to help construct problems, right? Because it has to satisfy this property. Let me show you an example. No, we're not quite there yet. I want to actually, yeah, so let's go ahead and think about this. So let's think a little bit about what kind of functions these may be. So let's think of this problem. Here's an example, and we don't quite have the tools to derive this just yet, but we will in just a few. We'll return to this. Let's think now. We have a particle, right? Let's go back to our particle in a room. And let's imagine that the room is infinitely large. Okay, let's not worry about the walls at all. Okay, the walls are really, really far away. We're concerned about the local behavior of our electron atoms. Imagine that you have an electron localized around the borders of the Earth, or rather the borders of North America. You can't go over the oceans, but when you're sitting in Nebraska, you don't see that. So think of it like that. We have this really, really big box. We're sitting in the middle and we want to look at what the electron or the particle looks like, what the wave function looks like now. So we don't have the tools yet to derive this, but we can come up with a wave function for this. So what I'm defining is what's called a free particle. This is an example. In a very large box, or effectively infinite box. Later, we'll think about boxes that are smaller. But now, just think of those. You're somewhere in Nebraska, and the edges are California and Virginia. You don't really know where the edges are. All right, what you can show. Well, let's think about it this way. So let's stop for a second. Let's just think of what the experiment may be, right? So let's ask this question, right? So here, we'll draw a line from the Atlantic to the Pacific, right? And then you're somewhere here in Nebraska. And since we're in Nebraska, I'm gonna, this guy is sleeping here because Nebraska's boring. And we've got a bunch of detectors near Nebraska, right? We've got some detectors for position here. These are our little position detectors. Little position detectors. All right, and so our board man in Nebraska is just sitting there monitoring his position detector. And he's got them spread out over the entire state. Okay, so this is hundreds of miles of detectors. There's a bunch of them, thousands of them even. And so let's think. So we have a particle that's completely free. Okay, so it's not interacting with anything. It has no preference to be near the Atlantic or the Pacific. Does not matter. The position is irrelevant. So what I mean by free is that free means no interactions with anything. So what that means is that in terms of position, there's no preference for the electron to be at one position or another. It's not biasing it in any way. The electron is freely able to move wherever it wants, anywhere it wants, does not care, right? And so what would we would expect our man in Nebraska to see when he does his ticks? Well, he should see over a long period of time an equal amount of ticks at every point, right? Because there's no preference over a long time where the electron is. It doesn't care. So ideally, what we expect to see is a probability distribution that is flat. Right, so this one, we see some ticks here, we see the same amount of ticks here, the same amount of ticks here, same amount of ticks here. Maybe there's a little bit of variance because of statistics. But in general, what he sees is kind of a flat top probability distribution. And he sees, again, remember this is psi squared. Psi squared is just a single value. Okay, no preference. This is no preference, no position preference. So now let's take that to the logical conclusion. Imagine he had infinite detectors. What is the functional form of the wave function? Well, psi squared is just a number, right? So we know that from this that psi squared has no positional dependence. It's just a number. We'll just call it A. Number, as in A number. All right, so now we have to think, okay, well, what's the function psi? If psi squared is A, just a number, and psi, what does psi look like? That's the wave function of psi. Well, we don't quite have the tools to build it yet, but I'm going to give you the answer. And then what we're going to look at is we're going to ask the question, why the hell is that the answer? And then I'll show you an alternate option, and we'll see that it can't be the alternate option, the more logical. All right, so the answer to this question is actually quite interesting. So the true solution is that psi of x, we're not going to worry about time here, is A e to the ikx, where I is the imaginary number, and k is a number. All right, we'll say it's called the wave momentum, but it's just a number. It has to do with the momentum, how fast the electrons go. So why the hell is there an I in this? And why is this the correct answer? Right, so let's think about this a little bit, right? So we don't even know what this, and we'll prove this next class, that this is in fact the correct answer. Why is there e to the I? What the hell is e to the I? Why is that the answer? What does that even look like? Right? And it turns out that there's a really, really special formula that was derived about 500 years ago that gives some very interesting information about what this function looks like. We'll come back in a second and calculate psi squared to make sure it works, but let's just look at this function first. So here's a nice note. Note. Euler's, this is what's called Euler's formula, named after Leonhard Euler, the famous mathematician from the 17th century. Want to derive this. And it's not hard to derive this equation. It takes a little bit of algebra. But he shows that e to the ix, let's just say e to the ikx, just to keep it simple, is exactly equal to cosine of kx plus I sine of kx. So e to the I, you would think e to the x, right? You think of something that's exponentially increasing, right? Well, obviously that doesn't integrate to 1 because it's exponentially increasing, it diverges. So you automatically, you're like, okay, well, that's a problem. But when you add an I to e, it turns out that it relates e directly to the trigonometric functions. This is a motion around a circle. Let me show you that. So we have this weird I. So what does this look like in terms of a coordinate? Right? How do we plot this in terms of x? Well, the way that we're going to do this, we can draw a two-dimensional coordinate for you. Right? And on the x-axis of this coordinate, I'm going to draw And think of this kind of like A plus I and some number B, a real number B, right? A plus BI, it's a complex number. And I'm going to draw on the x-axis the real part, which is the A component, and the imaginary part, which is the BI component. And then what I'm gonna do is I'm gonna plot b to the ikx as a function of x. So I'm gonna like x is time, if you will, and I'm gonna see how this function evolves in time as x increases. So let's start with x equals 0. So cosine of 0 is 1, sine of 0 is 0. So this whole thing is 1. Okay, so in terms of complex numbers, x equals 0 corresponds to a wave function that's just a number a real number, which is 1. So at x equals 0, the function lies on the x-axis here. 1. That's x equals 0. 0. Okay. So let's go, right? We're doing cosine and sine, so let's go by pi over 2. So let's go to cosine pi over 2 instead. Kx is equal to pi over 2. This is 0. This is 1. Sine of pi over 2 is 1. So the total thing is 0 plus I times 1, just I. So the imaginary component is 1. So the function now is here. This is at x, kx equals pi over 2. Right? And you can kind of see what's going to happen here, right? So at pi, it's here. At 3 pi over 2, it's here. And the whole function just goes around in a circle. I'll adjust my axis a bit. This is at kx pi. And this is at kx equals 3 pi over 2. And the whole function is going counterclockwise around this circle. So what's happening is that the system, as it's propagating through space, it's the behavior of it's almost as if you have an object that's, again, it's moving in this direction, right? So you have this electron that's moving in this direction. And as it's doing it, it's oscillating in 2 directions. It's oscillating in the real direction. So it's longitudinally going like this. The electron is moving up in the wave function, right? Not the electron, the wave function. If we think of the wave function as an object space, the wave function is moving up and down along the motion and up and down like an oscillatory wave in the longitudinal direction, which is along the axis of motion, going back and forth. And at the same time, transversely, which is the imaginary, it's oscillating like this. Right, so the electron is moving like a longitudinal wave, which is like a wave in water, but it also has a transverse component, which is the imaginary part, which is perpendicular motion. The electron, so any particle, the free particle, the atom, electron, photon, anything, is a wave, acts like a wave in free space that has a longitudinal and a transverse wave. Right? What are some things that have in real life that have longitudinal transverse waves? All right, so waves in the water, right, waves in the water propagate up and down along the direction of the motion, right towards the shore. Okay, so these are water waves are longitudinal. The water isn't expanding left and right perpendicular. It's not. You don't have a wave going like this and everybody's going out like this. But an earthquake, for instance, an earthquake has longitudinal transverse. Earthquake happens, there's a propagating wave that propagates out across the earth, right across away from the epicenter. And also there's some strain and tension in the transverse direction, which is where the wave is propagating like this out, and then the earth is actually vibrating in the perpendicular direction, which is actually the thing that's really destructive about it. So it's not this that really, right? The earth will undulate up and down like this. And that's not good, especially if it's a big amplitude. But what really kills buildings is the fact that they're also going like this, perpendicular to the motion of that longitudinally. And that's what's really destructive. Every particle in free space works exactly the same way. There's a longitudinal component that's oscillating, and a transverse component that's oscillating. There is one object in particular that has this property. So let me just say that. So let's just say this is the conclusion that the particle is like a wave with two perpendicular oscillations in the longitudinal and transverse directions. Just like an earthquake, or even more importantly, like light. The electromagnetic field has this behavior as well. There's a longitudinal component to the electric field that moves along the direction the light's traveling. And then there's a perpendicular transverse oscillation, which is the magnetic field. The magnetic field is perpendicular to the electric field. So if the electric field is propagating in this direction, the electric field is propagating in the transverse or the perpendicular direction. There's a reason why this behavior, right? This behavior, I haven't specified anything about the particle. I haven't specified the electron, atom, photon, which is a light particle, anything. This is true for all microscopic particles. And that's why we see light like that. Light has a transverse wave and a longitudinal component because everything microscopic has a transverse and longitudinal, including electrons. So again, let me just write that. So this is moving in this is parallel to the x direction. That's what parallel means. And this is perpendicular to the x direction. Perpendicular motion sine wave. This is where that wave particle duality stuff starts to appear, right? Where we notice that a white and a black electron can, right? Electron can exist in the black and a white electron simultaneously. Well, that's perfectly logical. If you think of the white electron being some type of wave and a black electron being some type of wave, there's nothing wrong with adding two waves together. We do it all the time. That's how you make music, right? It's just frequency synthesis, right? That's how a synthesizer works. You have solutions to a string that are your A and your B and your C and your D notes. You can also have a chord, which is 2 or 3 notes at the same time, right? And that's also a perfectly valid solution of your string or your vibrating device, just like with color. White is a wave, black is a wave, so you can make a chord that's black plus white. So this wave structure is built into everything. Right. I've kind of moved away. We've kind of talked a little bit about this imaginary. So maybe hopefully I've convinced you that there's something meaningful about this complex nature. But let's go back and look at the probability density and make sure everything works. All right, so let's just convince ourselves for now, we're convinced for ourselves for now, but this is a reasonable solution to the problem. But let's think if there's maybe an alternative solution. Right? Maybe we don't have to worry about complex numbers. Maybe we're just making our lives harder than we need them to be. So let me just copy this over again. I'll make a new slide for everybody. Getting a little busy. Right, and my claim here, is that psi of x is a e to the ikx, which is a times cosine kx plus I sine kx. Like that. Now let's ask the question, when I square this, do I get a single number? Well, complex numbers have a special rule. When you multiply a complex number by another complex number, you have to, I mean, you can certainly just multiply them together, but complex numbers have an ambiguity to us in real space. Let me go back again to the picture of our circle, right? I said e to the I kx is this motion counterclockwise in phase. This oscillation is counterclockwise. Well, if I do e to the minus I kx, I get the same circle, but now I'm moving around the circle in imaginary space the opposite direction. E to the I kx is counterclockwise. And then I'll just really quickly put it here. E to the minus I kx is clockwise motion. So if I multiply, instead of multiplying e to the I kx and squaring it, what if I multiply e to the I kx by e to the minus I kx? Well, what I'm going to do is I'm going to cancel out the oscillatory part of the equation, right? The oscillations are occurring in complex space. There's a reason why they're called imaginary numbers. They're imaginary in the sense that we can't observe them, right? We don't live in a complex world. Things move in a complex way. So we want to project this motion in a way that's real. We want to get rid of all the eyes, because we're never going to be able to measure an eye. Something may move with an eye, but we only measure the real part. So if we instead take the motion, the oscillatory motion in one direction, and counteract it by multiplying with a wave that's moving in the opposite direction, we can negate that oscillation, right? So as this moves this way, this cancels out by moving it the opposite way. So let's try that. Just try both cases. Right? So psi squared, there's two options. One is that we could just take e to the I kx and square it. Well, we would typically do with a function, but this doesn't get rid of the I. Right? We get a squared e to the 2 I kx. So what we've done, when we've multiplied it, we haven't done any sort of cancellation. What we've done is we've made it rotate twice as fast around the circle. Now it's moving 2x times. Right? So it's gone from going like this to going like this. Because now it's 2k frequency, 2kx sine 2kx sine. Now it's moving twice the frequency. That's not what we want. So instead, let's try multiplying it by its complex conjugate, its opposite, we call it. Well, what is that? Well, that is a squared, and then we have e to the I kx times e to the minus I kx. And of course, that cancels out, right? This is equal to a squared e to the I kx minus I kx, which is a squared e to the 0, which is a squared. Right? And that's exactly the right answer we want. This is what we observe. Right? This value right here is a squared, like I predicted. All right, so in order to calculate psi squared with these complex things, we have to multiply it by this object that's moving in the opposite direction. Okay, we have a term for that. Great, I got 5 minutes, just enough time to finish this up. So more precisely, the normalization condition for wave functions is the integral over the box of this value psi star, I'll give you the definition in just a second of what this is, times psi. I'm going to change the star to a cross. I will occasionally use both. Dx is equal to 1. Where psi cross, psi dagger. Now, sometimes I'll write psi star. If you see either of these, it's the same thing. Psi star is the so-called complex conjugate of psi, where all i's have their signs flipped. All right. So anytime you have a complex function, and there'll be a lot of situations where we don't even have to worry about complex numbers, it won't matter. But if you have something that's like PZI-KX and you want to take the complex conjugate, all you do is take it and put a minus sign in front of the I. Easy as that. That's all it means. And again, all that, and as you saw, that all that means is that now we're averaging over the complex space in the opposite direction. Okay, so one is moving clockwise, one's moving counterclockwise, and it's just a negative sign. So if you have a number a plus bi, and you do the complex conjugate of it, this is just a minus bi. Okay, just change the I. Meanwhile, note, if psi is real, psi dagger is equal to psi. All right, and we get that psi squared back. Because there's no i's in it, we're not flipping anything. There's no motion in the complex space, so we're not going to flip opposite. So well, sometimes we'll need to use complex numbers, sometimes we won't. And let me just prove to you in the last 2 minutes why we need complex numbers still. Why couldn't we choose something else? Right? Very, very easy argument. Remember, let me just zoom out in case you guys need to catch up. Remember that what we observed is that there's no preference which position the electron is at. It does not care. It's equal probability everywhere. What if we just chose the real part of this equation? If the wave function is cosine plus I sine, why can't we just get rid of the I sign, just make it cosine? That seems like a reasonable thing to think, right? Why can't we just use the cosine part of this? Well, what would psi squared be if it were cosine? So let me just read. If psi were equal to a cosine kx, what's psi squared? A squared cosine squared kx. And what does cosine squared kx look like? It don't look like a flat line, I'll tell you that. Right? It oscillates. So we would expect a probability distribution function that oscillates like this. Something like that. Right? This is cosine squared. So that would mean if I had a detector here, all right, think about my detectors. This is x sub I. I get lots of intensity there, and then no intensity here, and then lots of intensity here, and then no intensity here. Right? There are places where the probability is different, right? Probability varies with position. Right? So it doesn't work. It does not match our experimental results. If this were just a cosine function, meaning it's just a longitudinal wave going like this, you get the wrong result. It would imply that there are certain parts of the box or certain parts of America that the electron is never present. But what we see is that it's present everywhere with equal probability. Therefore, it has to be complex. Has to be. The only way to get that value is that all the oscillatory parts cancel out. And you just get the coefficient. So there must be an I in here. Right? So that means by definition, not only is every particle have a longitudinal and transverse component like light, but everything does. And complex numbers, this is why I don't call them imaginary numbers in this class. Because they're not imaginary, they're real. Here's a real reason. Because we can observe that things that propagate using complex values. Right? With a complex value function, it acts like one. The physics of it are its identity is complex, but it's stupid to call it imaginary. It's real. Right? So that's what a wave function is. Right? So we understand now what a wave function is to some extent, what it measures. And so now what we have to do in next class on Tuesday is understand what our box is for functions. So what does our matrix become? Like we understand vectors become functions. What is our matrix? We'll do that on Tuesday. Yeah, have a nice weekend, guys. We'll see most of you tomorrow. Thanks, guys.
Yeah, so, I was teaching them molarity today, right?
Yeah.
So I wore my mole leader
Love it.
shirt.